Loops are a powerful control flow concept that are used to repeat a set of instructions multiple times. If we imagine a plane where there exists a movable cube, suppose this plane could be partitioned into a grid of equal parts, where the cube can only move one section at a time. The objective of this task is to move the cube until it reaches the gold star. In order to reach the star, we may call a function that moves the cube up one square at a time, and repeat this until a cube reaches the star. However, repeatedly writing this function can become laborious, especially when the distance between the cube and the star is large. Instead of writing this function multiple times, we can place it inside a loop, and specify exactly how many times it needs to be called until the cube reaches the star. There are several different types of loops used, but the core structure is fairly similar between them. The main elements of loops consist of a condition, or a statement, that determines whether or not to enter the loop. Inside the loop is its body. This is where the instructions are placed. Every time we enter the loop, the set of instructions are executed, and this repeats until a condition is broken. First, we test the condition to check whether or not we enter the loop. If the condition is satisfied, the loop is entered, and everything within the loop body is executed. We then return to testing the condition, and decide whether or not to enter the loop again. This cycle repeats until a condition is broken, upon which we exit the loop, stopping the process. Traditional for loops follow a similar flow, with some slight differences. This type of loop often contains two additional elements that are linked to a control variable. The control variable is used to specify the number of times we enter the loop. The control variable is initialized, meaning that we give it an initial value. This is usually set to 0 or 1. The control variable is then tested within the condition statement, and similar to before, if the condition is satisfied, we enter the loop, and execute the code within the body. Following this, before returning to the condition, the afterthought occurs. Here the control variable is adjusted in some way that may result in a different outcome when retesting the condition. Again, the cycle repeats until a condition is not satisfied, at which point we exit the loop. A simple example of using this type of loop is if we would like to print the numbers from 1 to 3. To do this, we could initialize our control variable I to be an integer with an initial value of 1. We then set the condition so that we only enter the loop when I is less than 4. The afterthought here is a common shorthand notation to increment I by 1 after executing the loop body. Therefore, the control variable will only transition across the sequence of integers from 1 to 3. Initially I is set to 1. Then upon entering the loop, its value will be printed. The value will then increment to 2, and since the condition is still satisfied, we re-enter the loop and execute the loop body. This occurs until the number 3 has been printed. At this point, the control variable would have increased to 4. Now, it no longer satisfies the condition, and therefore we break out of the loop. Knowing how traditional for loops work is useful when we compare them to while loops, which are essentially a simplified version. A typical while loop contains the same structure, but drops the initialization and afterthought, since for this type of loop the condition may or may not be dependent on the control variable. However, we can simply recreate the for loop structure using a while loop by including these additional steps and placing them in the order in which they appear in the for loop flow. The flow of these two structures is identical. The difference between for and while loops can be demonstrated by revisiting the example of the moving cube. One way to move our cube to reach its goal would be to use a for loop, setting our control variable such that it enters the loop 9 times, and for each time it moves the cube up by 1 position, eventually reaching the gold star. As an alternative, we could recreate this structure using a while loop that takes the same flow, initializing our control variable to be 1, and then after each iteration we increment its value. This repeats until a condition is no longer satisfied and the cube reaches its destination. Say we forget to increment our control variable. Instead of stopping when reaching the star, the cube continues to move up since the condition is always satisfied. This will continually move the cube upwards an infinite number of times. Although these loops can be used interchangeably, they do serve a different purpose. In this example so far, we have focused on setting the number of times the cube moves up to be fixed. This is because we know the gold star is 9 positions away. However, we may not always know exactly how far away the cube is, and therefore it may not be practical to set a fixed number of times we enter the loop. In this situation, it would be more preferable to use a while loop. Here we could write a function that checks whether the cube is in the same position as the star and uses the outcome to test the condition. If the star is absent, the function would return true, and we would enter the loop again, moving up to the next position. This process would repeat until the cube reaches its final destination. At this point, the function would return false, since the star is present. Going back to looking at different types of loops, it's worth exploring iterator-based loops, which do not explicitly depend on a control variable. Instead, they operate by iterating over a set of objects that might not necessarily be an ordered set of numerical values. For example, if we take an array or set of shapes, we are able to iterate over every shape in this set, meaning that for each new element in the set, we execute the loop body. Each time we enter the loop, the current element can be used within the loop body. We can make the shape appear and then crumble to pieces. Knowing the basic structure of loops is a very powerful tool, since they are used across different programming languages. Although the syntax may differ slightly, the core concepts do remain the same.